This is a model of a 2 degree of freedom linear system, rectilinear system, and it'll illustrate two things. It'll illustrate that we have two modes of vibration, two frequencies, but also it is one of the most difficult things to physically model, although it is a favorite model used in vibration techs. They love to work this model because it's the easiest 2 degree of freedom model to solve. We have two masses. They're made of washers, and then we have 3 springs. I call this a coupling spring because it ties these two together. And we can easily see that we have two distinctly different modes of vibration. The first one is when the two masses are going up and down together. That's the first mode of vibration. Right. The second mode of vibration is when the two are going in opposite directions, and it's quite a bit higher. Unfortunately, we have some lateral motion in here. Now then, I can excite both of these modes by giving one of these an initial velocity start, which should excite both modes. And you notice in this case is that they appear to be taking turns stopping. Again, it is the case of two modes very close together in frequency, and the reason they're close together is because the coupling spring is fairly weak. The other reason is because that's the way the characteristic equation works out. But now then, as I said, we have a lot of lateral motion here, so one could almost say, well, it could also illustrate lateral vibration of masses on a spring. But this is a difficult problem for which to build a model. I have another model here, a 3 degree freedom system, and again, theoretically, you can illustrate the 3 modes of vibration. However, there's so much friction in this model because of the guide that is used that it's difficult to see the modes for more than a split second. So the students made a valiant attempt to build a 3 degree of freedom rectilinear model. The only successful model that I've seen like this is one using an air track, using air bearings.